Margaret is a PhD candidate in the Department of Astronomy and Astrophysics at the University of Toronto. She was born in Nigeria, did some of her studying in the Cameroon, and a master's degree in astronomy and astrophysics at U of T. And you'll see her interest is cosmology. This is the abstract that she sent us. Astronomers currently trying to understand some gaps in our knowledge, the history of the universe. And I'm interested in filling in the blanks in the Epoch of Reionization. That's a period in the expansion of the universe, which I'm sure we'll hear more about. Using computer simulations and then later data from the Simons Observatory, I'll discuss how we work towards understanding some fundamental questions about the Epoch of Reionization and how big the first stars were and how long it took the universe to reionize. Thank you. I'm sure it's going to be fascinating. Over to you.
Thank you. Thank you all so much. I'm really excited to be here and to meet with all of you. Before I begin, I would like to acknowledge the land briefly. So I'm speaking to you from Toronto, and I wish to acknowledge the land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and most recently, the Mississaugas of the Credit River. Today, this meeting place is still home to many indigenous people from across Turtle Island, and I am grateful to have the opportunity to walk on this land. I'm so delighted to be with you all tonight, and I wish this talk was happening in person, but I look forward to visiting the beautiful Sunshine Coast sometime soon. So I'll be talking briefly about my research in the next few minutes, and then I'll talk a bit about an outreach program that I'm involved with. To begin, I would like to go very briefly through my journey as an astronomer. Like most people, I became very fascinated about the night sky at a very early age. This led me to study physics and astronomy at the University of Nigeria. And for my undergrad thesis, I worked on building a 2.4 meter radio telescope from locally sourced materials, like as shown in this image. After my undergrad, I went to the African Institute for Mathematical Sciences in Cameroon, where I studied the evolution of supermassive black holes when they merge. This was supposed to be a video, but I think. I moved to Toronto in 2016 afterwards for a master's in the University of Toronto, where I studied, one of the projects I did for my master's was to study the kinematics of galaxies. And for this work, I had to travel to Arizona to use real telescopes, and it was really awesome. I continued on for my PhD studies here in Toronto, and for my PhD, I decided to do something completely different. I decided to go into cosmology. This is a slide that comes up in every cosmology talk. It shows the history of the universe from the Big Bang on the right to the present day on the left. The universe starts off very hot and opaque, and as it expands, it gets to the point where the simplest, it cooled to the point where the simplest atoms could form. And this meant that light could now travel to us without bumping into any electron. And that light has been traveling to us ever since. This is the origin of the cosmic microwave background, the CMB. And as the universe continues to expand and cool, more and more of these atoms begin to clump together until the very first stars could form. These stars produce radiation that caused a transition from a cloudy, non-transparent, opaque universe to a transparent and ionized universe. And one of the outstanding challenges in cosmology is understanding how this transition took place. This transition is called the Epoch of Reionization. And for my PhD, I am concentrating on studying this epoch, and this epoch is highlighted in the blue, is shown in the blue box on the screen. Here is a video showing how we think the transition progressed. Our current model assumes that this transition happens by the four stars giving off their radiation in bubbles. So the bluish, the white regions you see are the stars giving off the ionizing radiation, and the bubbles grow and eventually overlap until the whole universe becomes ionized, becomes transparent. I'll just hold on until it finishes playing. Okay, some of the big questions for my thesis are listed here. I'm interested in knowing how and when reionization started, how long it took the universe to go from neutral to ionized, and so on. So the cosmic microwave background, the CMB, is the glow of the heat left over from the Big Bang, and it fills the universe. The color differences on the CMB represents very slight temperature and density differences in the early universe. And as these CMB photons propagate through the universe, as they travel to us, they interact with matter that they meet along the way. And about a few percent, I think about 5 or 6% of these photons will be scattered by electrons in the intergalactic medium and in the intercluster medium. And they leave an imprint on the CMB temperature that we can measure. These imprints are called secondary anisotropies in the CMB, and they contain lots of information about structure formation, and in particular about the Epoch of Reionization. Some fraction of these CMB photons will be scattered, and they form an effect that we can use to learn about the reionization. So the effect is known as the Sunyaev-Zeldovich effect. In particular, we can study this effect because the CMB is distorted. So the CMB, the kinetic Sunyaev-Zeldovich effect probes the epoch of reionization, and this effect describes the distortion of the CMB as a result of the relative motion of free electrons and the CMB photons. So from this image, as the CMB photon is traveling towards us, it interacts with the electrons that surround these four stars, and we see a decrease in the CMB power because the electron is moving away from us, and vice versa. The total KZ contribution comes in two parts. One from high redshift, which probes reionization, and the other from low redshift, which we call the late time KZ effect. But only to learn about reionization, only the early time KZ is useful to us, and we have to think of ways to disentangle these two components. However, the KZ signal is a very, very small signal, and this signal is small because the probability of a photon, of a CMB photon hitting an electron is very, very slim. This probability increases very slightly when there are more electrons around, as in the case of the reionization scenario. And So to measure these KZ signals, we need very, very sensitive experiments. And this brings me to talk about the Simons Observatory. So for my work, I will be using data from a telescope, an upcoming telescope called the Simons Observatory. The Simons Observatory is a new generation observatory that is being built in the Atacama Desert in Chile. The high resolution data that we will get from this telescope will be very useful and help us to understand and answer questions about the early universe, such as the Epoch of Reionization. The Simons Observatory consists of over 200 scientists from more than 40 institutions around the world. But while we wait for Simons Observatory, right now, Simons Observatory is on track for first flights to begin operation sometime in 2022. We had a delay because of COVID. But while we wait for data from the Simons Observatory, we can begin to use simulations to forecast how well the Simons Observatory will be able to constrain parameters of reionization. And the simulation I use takes in 3 main parameters. And these parameters include the mass of the stars that are causing reionization, the mean free path, which is represented by lambda here, which the mean free path is just the distance that the photon travels, and the ionization efficiency is the number of atoms that are ionized in each halo. And again, these bubbles, these white bubbles begin to grow and overlap until the whole universe is ionized. So these 3 parameters go into the simulation, and we can then get out 2 parameters that tell us about reionization, which are tau, the optical depth. The optical depth serves as a means of quantifying the time when reionization started, and delta here is the duration of reionization. So we use a technique called Fisher formalism to forecast constraints on these parameters. Before I go into the constraints that we have forecasted, I'll first go briefly through some statistics and define what a likelihood function is. So the likelihood function is given by this formula at the top. It is just the probability of getting a certain piece of data given an underlying theory. So we want to ask ourselves how likely it is that we got a measurement given that the universe is described in a certain way. The figures you see are plots of likelihood as a function of some parameter that I've called alpha. So we would usually like our likelihood function to have a very sharp peak like this one on the top, meaning that at some value alpha naught, we are very likely to get our data. So our data will be inconsistent with alpha as any other value. But we can also imagine another likelihood where the distribution is very broad, like this one at the bottom. There is a peak. There's also a peak at alpha naught. But there's also a good chance that we can recover the data at some distance alpha away from alpha naught, even though alpha naught is the true value. So what we want to do is find a way to measure the width of these likelihood functions, or some way to measure how fast it falls off from the maximum. And so if it falls off very quickly, like the one at the top, then we know that our data is constraining. So we report constraints on parameters in plots like this on the right. This is called a contour plot, and they represent one sigma and two sigma constraints on whatever parameter we're measuring. And these 1 sigma and 2 sigma constraints can now be calculated from the Fisher formalism. And now we begin to get a sense of why and how the Fisher formalism is useful, because the bigger the value of the Fisher matrix, the smaller these contours get, which means that our data is well constrained. And so now I get to some results. We do all of this that I've just talked about, and we forecast constraints on 2 reionization parameters, the ionization efficiency and the main free paths of the photons. And we keep the mass of the ionizing sources constant at the value of 10 to the power 9 solar masses. And as you can see in this plot, our contours, which are the dark blue and the orange one in the middle, they are a lot smaller than previous measurements, which is represented by this light blue line around the plot. And so we are optimistic that when we get data, when data finally comes from the Simons Observatory, we can narrow down the values of these parameters. And going forward, we do basically the same thing. We added a few tweaks, but at this time we are able to forecast constraints on tau, the optical depth to reionization, which tells us around what time reionization starts, and parameter delta Z, which gives us a sense of how long it took the universe to reionize. And the takeaway from this plot is the black curve in the middle. These are the constraints that we forecast, and we see here that our constraints are getting really tighter. Okay. Okay, so just to show how well we do in this plot, I have our results from the previous slide at the top here, and we show errors. We show our forecasted error and compare them with previous measurements, and we see here that our value is a lot smaller than all the other ones that have been measured in the past. And so we're really narrowing down on the actual value of these parameters, which is good. Okay, and so as a summary for the science bit, we are hopeful that upcoming telescopes like the Simons Observatory will open our eyes to understand details about the reionization epoch. Okay, so briefly, I would want to talk about the Pan-African School for Emerging Astronomers. And this is a program that I've been involved with in a while. PASI, Pan-African School for Emerging Astronomers, which we call PASIA for short, is an innovative short course for astronomy, a short course in astronomy for African university students and school teachers. And this school started in 2013 in Nigeria and has run biannually since then. The next school was supposed to be this year, 2021, but we've had to push it forward due to COVID. The main goals of PASIA are to build a community of astronomers in West Africa. So the school started in West Africa, but has now evolved to the whole of Africa. And so our goals still remain to build a community of astronomers in Africa and to empower young Africans in becoming scientific leaders. And we also share ideas about how teaching and learning of science is done. The team, PASIA, has a team of instructors that come from various places in the world. This map shows, the red colored regions shows some of the countries that our instructors come from. So we are made up of an international team of instructors that commits their time and energy to this goal. PASIA has two streams that run concurrently. We have an undergraduate stream, which includes teachers, and we have a postgraduate stream. Undergraduate students mostly learn about diverse astronomy topics like the solar system, radio astronomy, and cosmology. And they learn about these topics mostly through interactive co-taught lessons. They also develop an astronomy outreach activity for their own communities after the school. And one of the highlights of the undergraduate stream of the school is a 2-day inquiry activity on distances in the universe, as shown in these images. In inquiry-based teaching, students learn science through a hands-on challenge about parallax, and I'm going to show a video in the next slide about this. And students mostly ask their own mini research questions and investigate the questions in teams, and then as we can see in the slide, and then they share their findings to the bigger group. So I would have to switch my tabs quickly so that I can play the video. In this video created by Alison Rose.
Is to measure the distance to the balloon, but you cannot walk over there. Not to tell you the answer. Our job is to basically guide you, help you if you get really stuck.
So here we see that the students are participating in the inquiry activity.
So if we can imagine that that's from that point to that point. This cause, I don't know whether I'm making a mistake or the very. We're taking this distance. So where is it on the ground? Yes. So if it is here, let's put and let's guess it. Let's see meters in here. This is that. When you look at the house, it's not in line with the planet. Like when you stand at this point, it's in line. If they say, so we will get to the objects. Yes. Yes.
Okay, back to my slide. So this is That was just a clip from the 2017 school we held in Ghana, while the students were participating in the inquiry activity. Okay, so we mostly teach about astronomy topics in the undergrad stream, and they have this inquiry activity also. But in 2015, we realized that these skills are very fundamental. What we teach, they are very foundational and necessary, but they are not sufficient to build a well-rounded scientist. And so in 2017, we introduced a postgraduate stream that is now held in every school. The postgraduate program is designed to equip students with skills, the knowledge and the thinking patterns that are required to develop into a professional astronomer. And the topics we cover mostly include Python programming, how to do observation with telescopes, how to process data, and how to analyze data. This is in 2017, we held the school in Ghana, and the postgraduate students used the 32-meter telescope shown in this image to analyze, to observe the universe. Okay. To help the instructors develop the interactive teaching and the inquiry skills, we usually hold an instructor workshop the week before each school begins. And we usually organize the instructors into international pairs, and these pairs co-teach the interactive classes together. And this helps the team to exchange ideas about teaching and facilitate how to teach science. The school also, so the school mostly targets university students, but at that point, students in the university mostly have a clear path about their career plans, and we understand that most students are not aware of astronomy as a career option from an early stage. And so instructors also spend a day in the week engaging in astronomy outreach to local schools around the host city, mostly high schools and elementary schools. And the students are always very excited to look through telescopes, and they usually have lots of questions. Like you can see in these images, students are taking notes when an instructor is talking about an astronomical object, and they are usually so excited. So the school has run for 4 years now as a West African school first, and now we're expanding to the rest of Africa. But after 4 iterations, we have learned a lot. The school has over 250 students so far, and about a quarter of those identify as women from around 10 countries, I think. So with this population, we have enough to gauge the impact of the school. And in April of last year, we sent out a survey to the alumni. And from that, we learned that PASIA has impacted a lot of our alumni in their career and their teaching, since most of our students are also school teachers. Students have responded to the inquiry activity and to the school in general, saying that they now feel very empowered to do science. Some say that they are able to reason mathematically and think like scientists. Many have said that the inquiry activity was a key part of the school for them and has helped build their confidence in problem solving. And I especially like this quote from one of our students, and they say, PASIA has made me realized that I can think and find answers to questions on my own without external help. I can now say that I can think like a scientist. So we get lots of feedback like this from our students, and they help us to keep our motivation going. So this slide is my last slide. This is our social media handles. Please like us and follow us and share. We will update all of these pages with upcoming activities that we have planned. Thank you all so much for listening.
Okay, so my understanding is that when everything was ions, light could not get through. And so the universe was opaque, right? Then when the atoms started to form, then light could now escape, shall we say, now could get through. And that's what we see as the cosmic background radiation. Okay,
right.
But now what you're saying, this is a completely new idea to me, this idea of reionization. And it seemed to me that what you were saying was that at this stage in the universe, the whole universe became reionized again. But wouldn't that make it opaque? And therefore we wouldn't be able to see back to the cosmic background radiation. We would be looking back to the end of the era of reionization.
Yes, that is completely true. The only difference between the ionized universe then and now is that the universe has expanded a lot more than it used to be before. And so it's not as dense as it used to be. And so light can still pass through.
Okay, so then when you were talking about the mean free path of the photon, okay,
yeah.
Is that like an enormous distance? Like, you know, like galactic size distances, or are we talking about atomic size distances?
So that's one of the things I'm trying to find out in my research, the mean free path. I don't think it's a huge number like galactic size distances, but it certainly isn't atomic size distances. So when the picture, I think, is that you have these neutral atoms clumping together and they get so dense, gravity pulls them together, they become so dense until the core is hot enough for a star to be born. And as the stars are giving off ionizing photons, because all around the universe at that time is all neutral atoms, right? But as the stars begin to give off ionizing radiations little by little, these ionizing radiation, as they travel, they interact with the neutral atom and reionize that, right? And that means that they begin to travel further and further distances until the whole universe becomes reionized. So in the beginning, I guess the distance, the mean free path it's not a huge number because the photons are just traveling like nearby to meet a neutral atom before they ionize it. And then afterwards, when those bubbles become bigger and bigger, the mean free path is increasing. And this is also something that we are trying to understand about the universe, right? Because we don't know if these stars, this ionizing pockets, if they were like small and numerous, or if they were like large and scarce, right? Because that would impact the mean free path too. If we had like tiny bubbles scattered around the universe, which are overlapping quickly, then the value of the mean free path would be different, right? But if we have like huge bubbles of ionized gas that are takes a while for the universe to reionize, then the main free part will also have a different value.
Yeah, I guess I'm just trying to get a picture of like, this is totally new idea. And I'm just trying to get a picture of what we're talking about. We're talking about huge, massive stars, I gather, that are, generating the energy to reionize everything. And then in between, it's almost like air, just ordinary air, like hydrogen and helium. But and then are we talking about stars that are hundreds of light years apart, or tens of light years apart, or hundreds of millions of light years apart? I mean, what are we talking about? Yeah, I have no idea.
Yeah. So,
Is it basically a lumpy universe with lump, like stars are the lumps, and then in between it is this kind of very, very thin gas, and the thin gas is being ionized.
Exactly.
Okay.
Exactly. Yeah. So the current understanding is that these four stars are really massive, and so stars, these first generation stars, like we call them, are supposedly very massive stars, more massive than the stars that we have at present time. And that would probably mean that we had fewer sources at that time causing reionization, which would mean that the distances between the stars are huge if they are scattered randomly. But yes, this is all stuff I'm interested in finding out.
Okay. Thank you.
Thank you.